Good morning, everyone. I'm happy you got some coffee, so I can also wake up and buy this. Okay, so first, there's a small issue. We get these reports about the quality of the teaching, and some people like to complain. And at the beginning of the semester, some people complained about the homework, which we took into consideration. That is not a problem, of course, but just yesterday I got another complaint that there was too much homework, and I'm not sure what it's referring to. So I just want to say a few words on this. So first of all, at the beginning of the semester, my feeling, maybe you are correct, there was a lot of homework. Secondly, I don't think it is not justified, because I check your exams and I just was trying to help you with the technique, because when I check exams I see that the technique is not good. So thirdly, we do not have in this course a mid-semester exam, so I don't think the complaint is justified, but it's even less justified in my opinion now, because I think we asked to some decline in the amount of homework. So there was a problem at the beginning, or you can, and I think now it's not so bad. So what is my point? If you have a complaint, it's much easier that you come and talk to me, and not send me some email obscure that, or through the system, that there is a problem, because I don't understand the problem if you don't talk to me. If you talk to me, I might understand it. Just knock on my door and complain. It's fine to complain, okay? Okay, this is a small issue. I prefer direct communication and not indirect communication through some channel, which is complicated. Okay, so let us start. So what did we do last week? We were dealing with magnetic fields, and we introduced Biot-Savart law. And Biot-Savart law is similar to the Coulomb law, but for magnetic fields. The source of magnetic fields are currents that we call them J if they're in 3 dimensions, and then if it's on a 2-dimensional plane, it would be K, or in a 1-dimensional loop, it would be I. So there is a relation between these currents and the magnetic field, and this is Biot-Savart's law. Okay, great. What is missing? We have Biot-Savart is equal to Coulomb, so what is missing? In electrostatics, we had also what is electrostatics in matter. We had the polarization field. We don't have it yet in magnetic field. The polarization field will be replaced by something called magnetization field. And we will have different currents and related to this magnetization field. This is what we are going to discuss. What else is missing? In electrostatics, we had the electrostatic field and we had the potential field. And we still did not discuss the potential field, quote unquote, for magnetism. So what I'm going to do at the beginning is discuss the equivalent of the potential field, and this is called this field, which is called A, R, and T, in principle T, but for statics it will be independent of time, and this is called the vector potential. So unlike the electrostatics, the potential is not a scalar field, it is a function of the coordinate of the systems, and if you have it, then what? Let's say we have it, then the following is the issue. We know that div B is equal to 0. This was last week. This is the famous law which actually says there are no monopoles in magnetism, unlike div E that gave you the density of charges. Okay. So if this is correct, then we can say that there exists, mathematically, there exists some field A whose rotor of A gives you B. So we are replacing this vector potential with this rotor operation that we consider easy to do. This gives you the B. So if I know A, I know B, exactly like if I know the electrostatic potential, I know the electric field. And we do this, and this we will soon see, because we can analyze A in a way which is a bit simpler than the Biot-Savart law, which was very complicated because you had to integrate over the currents, and these integrations are in generally very complicated. So we are asking, what is the Poisson law for this field? So for electrostatic potential V, we know that we can define it up to a constant, right? Why is that correct? It's very simple, because div V, if you add a constant, then so what? And this is very common in physics. Energy shifts are common. Now we are dealing with an object which is different, because this is a vector. This A is different. So we can abuse it, quote unquote abuse, in a more fantastic way. It's not that we can add to it a constant. Of course, if we add A plus a constant, will give you the same B, right? Because rotor of a constant is 0. But there are a large, infinite number of functions that we can add to A, and they will give you the same B. That is the idea. And this idea leads to the question, what will we use? What will we use? What addition or what structure of the theory will we use? And this is related to something called gauge. Gauge. There are different types of gauges. Now I'm going to discuss a gauge which is called Coulomb. Coulomb gauge. You know the word gauge is in Hebrew kiyul. That is, I am defining this A in a very specific way, and Coulomb's gauge is a way to define it that the equations will be slightly simplified. There are other gauges. For example, the famous gauge is called Lorentz gauge, but there are actually an infinite number of gauges. You can choose whatever you want, but let us follow these great people, Coulomb and Lorentz, later on in the course, and choose in a clever way this gauge. And what is this gauge? This gauge says, this Coulomb gauge says, div A is equal to 0. So I'm choosing a vector potential A such that this equation will be satisfied. And then there are two questions. Why is this good? That's question number one. And B, why is it allowed? That are the two questions, and now we are going to discuss this kind of briefly. So, yeah, so I'll first explain why is this good for us, and then later it's also obvious why it's allowed. So, why is it good for us? What is the benefit for the Jews, as people say all the time? So, what did I use up to now? Div B equals 0. What is the second basic equation in magnetostatics? Is the equation relating B to J. We didn't use that, and that is going to be, of course, important. So let us look now on the curl of B. So the curl of B, we said already, we know what this is. This is U0 times J. This is known. This is from the previous class. So let us write down what we know. This is Uj. This is the density of current. It's a function of R in space. This is equal to curl. I write it like this time, A. Why? I just put in the definition of A. Now, what is the curl of A? Okay, let us look in some notebook, and this is equal to, I'm just telling you, but this is simple math, div A minus Laplacian A. So, in our choice, this is 0. And this is a good thing, right? Because then we got rid of one term. That's the reason why it's good. It's very simple. We get rid of this. But there is a second reason. What do you think about this term? This reminds you exactly of the Laplacian, and you are experts in Laplace. So the goal of one of the goals of magnetostatics, in principle, if you can, try to take the magnetostatic theory and put it into electrostatic theory, and then go back to homework number 1, where you solved a lot of questions and you are now prepared for this. So you know how to do it. So here is our Laplacian. And what is it equal to? This uj. So again, this choice is based on Coulomb gauge, but I can use it. I'll show you later why this is allowed. But if this is correct, I get the following equation, which is the central formal equation. There is a minus here, so this is mu 0 j. So you give me the currents in the system, let's say in a volume, in some, let's say in this table, and I'll calculate the vector potential with this Poisson equation, and then I can easily find B. That's the general idea. And as I said already, this is Poisson equation, but it's a Poisson equation with a small modification, because we have here vector A and vector J. But that is okay, because it's not one Poisson equation, it's 3 Poisson equations. But 1 and 3 is the same thing, and we can solve it kind of easily. So just a reminder, let us say we have the usual Poisson equation. So we have V minus rho. This is the density of charges, no currents. And this goes, what is the solution of this thing? This is what you learned in high school, right? This is the Coulomb law in disguise. It's nothing else. So what is the V? The V is simply, okay, you need to integrate P of R over the volume. What volume? The volume that contains all the charges, R minus R prime d tau, 1 over 4 pi epsilon 0. This is the potential. This was in the class, but this is very intuitive. You see here, the important part, this is for the potential, we have 1 over R minus R. This is 1 over R potential, and here we have simply the densities. So think about these densities as a combination of delta functions. This is simply Coulomb's law, nothing else. And this is the solution of Laplace. Okay, maybe you don't remember the proof that this is the solution, but it's obvious for physicists that this is the solution. And then, okay, this and this is the same. So let us do it and write down the solution of this A in a formal way, of course. We'll have here A. Okay, yeah, here is something annoying. Mu 0, which is the permittivity of the vacuum of the magnetic field, and this is E0. This one is on top, this one is on bottom, so here it will switch. Mu 0, the 4 pi will remain, and the integration now over the volume will have J R prime. So again, this is, I think you know this already, but if you don't, let me know. Shout d tau. And that is it. We finished the course of magnetostatics. This is the main equation. In principle, of course, I'm not claiming this is any necessarily easy, but you have either 3 components of A related to 3 components of J. And what is this? It's like Coulomb, 1 over R. And again, R prime is in the integration of d tau, and R is the location of where you are looking out in space, so A is a function of R. And of course, you can use this, and you can take the rotor here, get B, and so that this is compatible with Biot-Savart. I'm not going to do that, but this is okay. I'm telling you, it's even in Griffith's book, so you can. It's most likely it's okay. Okay, so this is a famous equation for A and J. But now, yeah. So okay. So to complete this, we need to understand a little bit. I think the new thing is, or slightly new. Maybe you heard about this a little bit before. Are these gauges? So how can I think about these gauges in general, not necessarily for Coulomb gauge. כן. פה? 3 יש פה. A זה וקטור.
לא, אני מדברת כאילו...
A וזה?
לא, במה שלמעלה גם כן.
זה הפתרון של זה.
אבל כאילו, מתי נשתמש בכל אחת מהמשוואות?
This is the equation. It describes the problem, and this is the solution. This is the nice thing here. I solved this equation, which is the Laplacian. This is the Poisson equation, and I solved it formally at least. This is the solution. This A and this A is the same thing. But here I have it as an integration. Give me J, do this complicated integral, you get A. That's it. It's a formal solution. So, yeah. So maybe you claim, maybe correctly, that this is just a formal solution. This is just an integral. I don't say what is this integral because you didn't tell me what is J. Give me J for a specific problem. This is why it's so good to be a professor and not a student. You find out what is the solution. For different problems, this can be terribly complicated. Most problems, it's terribly complicated. You cannot solve it. You can integrate it numerically, usually. In some special cases, you can solve this exactly. In general, we need to approximate it. We will soon approximate it. What will be an approximation that you can think about immediately because you know electrostatics? Yeah, the multiple expansion, because here you see this 1 over r, it's the same as in that. So let's expand, and let's say if I have a field here, some j here, I can say something very general on the field far away. But I cannot say really much if I have a kind of monster like this, you know, with some currents. I don't know what is the solution inside, right? I mean, it's impossible in practice as a closed form, but again, with the programs today, you can do this integration, and in many cases, with some effort. Okay, so this is the solution, and now we want to discuss, in general, not necessary for the Coulomb field, some issues with the gauge. So let's say I have an A, I have an A0, so, and then I want to add something to this field. This is what we actually did. What is A? A is some vector potential that gives you B. What is A0? Is also some vector potential that gives you B. So these are two different functions, but they give you the same B, B. And what we are going to claim now is that this A0, you can add a function like this. A general function, this depends on the coordinates, but it has to be this divergence of some scalar lambda. So this is a vector, and the reason for this is trivial, but you can write it in your notebooks. So we have rotor A is equal to rotor A0 plus rotor d lambda. This is of course B. This is you can think about, this is the new A that I construct from the old A. This is by definition B, and this one is 0. It's 0. This is something that you should remember from mathematics, but you remember it also from electrostatics. Because if I think about this as a potential field, a scalar potential field, like in electrostatics, what is this guy? This is the electric field. And rotor of E, that you should remember, is 0, because the charge Coulomb, as you had in high school, the field lines go outside, and the rotor of that is 0. But this is very famous. Okay, so I can always add this function to the original vector potential, and this is what I was saying before. For electric potential, I add a constant, and here I add some function, some general function. And this can be used now, let's say, so now we are going to ask, so what we are doing here, we are assuming that there exists some solution to this equation, which is, physicists, obviously, it's obvious that there is, and then I want to say, I want to go now to Coulomb, to the Coulomb gauge. So what do I need to do? Here I did the rotor to show that I can add something. Now to find the Coulomb, I need to say, let's operate with this operation and see what happens. Okay, so let's see what happens. I have div A, and I want it to be 0. This is special. This is Coulomb. This is equal div A0. And what will I get here? When I act on, I get the Laplacian, and we love Laplace, because Laplace is like, it gives you the Poisson. So we got now the equation for lambda. This is the equation for lambda. If you find a solution that satisfies this equation, then A is in the Coulomb gauge. It's clear? That's what I wanted to do here. And what is the claim? Let's say you found some solution, and of course in reality we don't find A0. We don't care about A0, but there is something that solves this. Let's say you are clever and you found it, you guessed it, or it's in nature. Then we are going to use this transformation. This is an equation, but we know the solution of this equation. What is the solution of this equation? Again, the same thing like this. So if I know A0, I can find the lambda such that I'm in the gauge field, in the gauge, in the Coulomb gauge. So we can find some lambda that will land us in the Coulomb gauge, and then we are very happy because of the simplification that we had here, and then we can use this and we are done. And what is this lambda? This lambda solves Poisson equation with a source. A source means a set of charges. Now it's really, lambda is a scalar, so this thing is also a scalar. So this is like really a charge density in electrostatics. So this is the meaning of the word source. It's a source of charges. You can think about them like that, with a source of charges A0. Okay, so we are done, and this is a good solution, and I explained why this is justified and allowed. So we can sum up some part, at least, of the electrostatics. Just for you, I like this triangle. We had this triangle also for the electrostatics, and now we have it for the magnetic statics. And it's just for summary, just for you to kind of see the structure of the theory. We have in the theory, we have J, and again, this J can be K or I. That's actually the difficulties. These are the currents that give you the magnetic fields. And from J, you can go to B. And as I just now showed, J is related to A, and also A and B are also related. So I'm not going to write down the equations again, or maybe I'll write only the simple ones, but if I want to go, in this direction, this is the Biot-Savart's law, right? This give me J, Biot-Savart, which is this integration over the current with the distance with all these vectors. So okay, I can go down in this direction. Can I go in this direction?
Ampere.
Yeah, this is simply ampere. We can, that is simpler than bias of art. I hope that they don't, they're not insulted. U0J, so ampere, not ampere, ampere. And to go from here to here, usually, actually, as far as I know, you always go in this direction, to be honest. You don't go from B to A. And maybe because A is not so, but it's not that it's impossible. You simply, if you want to go from B to A, you need to go like that. Or you need to think. But this is also trivial. This is this line. So if I have B, if I have A, this is just definition rotor A. And usually, but not always, we use the Coulomb convention. And if I want to go in this direction, then in this direction, the opposite direction, usually you want to reach the B, so you go here and then there. Then you have this solution that we just now wrote on the blackboard, mu0 for pi, which is a Poisson in 3D. J of R, dl, R, dimension -2, I like to write it like this, the volume. The dimension is 3. Okay, this is Poisson-like equation. So this is the summary up to now. You can kind of memorize it or look at it a bit more, and maybe this will what will stay later on in your life. So now, as I mentioned, the solution, this solution is horribly complicated, but there is a hope. If I look at distances, if I look at distances which are large, so I have a body and there are currents here, and I'm going to look at large distances, I can say something on this A. And this will be done with the same technique as done for the potential, because here I have R minus R prime with something called the multiple expansion. So I'm not going to go into the whole details because it's very similar to the previous one, but there are some differences. What is the most striking difference? I mean, the simplest difference? One issue is its vectors, but there's another point. What is the leading term in principle of the...
there is no zero term.
There is no zero term. And now the question is, we know this because div B is equal to 0, so there's no leading term. But now let us see how this comes out automatically. And this is related to this integration here, that there's no monopole. This is something obvious that shouldn't come up. So let us see these things, and let us see the similarities and slight differences compared to the electrostatics expansion. So this is the dipole expansion, the multiple expansion. So what is the multiple expansion? We look at large distances. Okay, so multiple expansion. So the idea is the following, just a reminder of the notations. We have some body. In this body we have some currents, J. It's again very formal. And we have some origin, and then we have some distance, which I'm going to call R vector. And here I put the observer. So eventually we want to know what is the magnetic field at this point here, R. And of course it depends on all the currents that are in this system here. And I'm doing it for a loop. So the structure that is creating this is a loop, but it's more general. Then I have another vector, which is R prime. Here I have some I Of course, in principle, I could use Bio-Savart and integrate, but I'm not doing that because now I'm going to give you an explicit expression, provided that this R is big compared to the size of the system. So R, think about R, this guy is standing on the moon. Well, not really, because if it's on the moon, you cannot measure the magnetic field, but far away compared to the size of this object. And this angle here is what we call theta prime. So, of course, there is a distance here, which is r minus r prime. And this is actually the distance that enters here into the equation. And what is the multiple expansion that we already had, which is based on what? It's based on simple, it's based on two things. It's based on the cosine law, because here we have an angle and then we expand it with this angle. This is a reminder. And it's based on a Taylor expansion of this 1 over r minus r prime. Again, r is big. And this we showed already. This is 1 over r sum n equals 0 to infinity. And then we have r prime over r to the power n. And then we have the Legendre polynomial cosine theta prime. So, for example, P1x is equal 1, P0x is equal 1, P1x is equal x, etc. These are the famous polynomial Legendres that you already know. Okay, and now I can use this expansion in the equation for A. So things look very similar at this stage to the usual expansion. So now I'm using, so the equation that we had on the blackboard was for J. Now I'm switching it a bit because I assume that the current is on a loop. So it's not delta tau, it's now I'm going to integrate over the current, let's say, is in this direction, and I'm integrating over dl prime. So these are vectors, so I have a vector, 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 vector. I'm summing them up and calculating for each position this theta prime, this r prime, and this relative coordinate. This is what I need to do in order to get the A. So I'm doing it with an I, not with a J. And so delta tau, this was in previous lesson, I replaced delta tau with integration over delta L. So all is left to do, so this is an integration over the wire, over the geometry. It's not an arbitrary object, this is this object, whatever it is. I'm integrating along here. And then we have Coulomb's. Okay, yeah, I still didn't do the expansion, and here I have dl vector. So I'm integrating. Of course, if I didn't have this here, what would be the integral? I integrate 0. And this you'll soon see, that is important. So this is what I need to calculate. And what do I do in practice? I plug in here the multiple expansion for pi sum n going from 0 to infinity. 1 over, I'm a bit taking this outside r to the power n plus 1. And I'm leaving inside this r prime the power n pl cosine theta prime. This is pretty nasty. dl vector. So the leading term when r is big, without being too rigorous, is what? Is n equals 0. So when r is large, leading term, what is this? This is called the monopole. It's n equals 0. And you see, when n is equal to 0, this is 1 over r. This would be like a Coulomb field that decays like 1 over r for a potential. Okay, it's a vector, but, and we already said this has to gauge. So a monopole, again, that means the term that with n equals 0 is u0 I 4 pi, then this is 0, this is not L, this is N, this one is 1, so all I have here 1 over R, but then I have integral over the wire of dl. So I'm integrating over a while, dl, 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 all these vectors, I'm summing them up, it gives you 0, as was already mentioned. This is 0. And this is not surprising, because there's no monopole. And this, if there was a monopole, what would happen? Div B will not be equal to 0, right? So this is as expected. But now we see why. It's because the integration over this wire, closed wire, as expected, no monopole. Why? Because we don't have magnetic charges. This is because div B equals 0. If we had charges on this side, this would not be correct. But we don't have these charges in nature, as far as we know. Okay, so if the monopole is 0, what do we need to do? We need to go to the first term, then we can have a break maybe, and Coffee will be happy. So the first term after the monopole is called the dipole. And that it is what it is. It's the dipole, so okay. And now maybe you see why I think in electrostatics maybe it's a bit surprising that we talk so much about dipoles, right? Because the charges are stronger than the dipoles, so why do we talk about these dipoles? But now in the magnetic field, because there's no monopoles, we talk only about the dipoles. And the dipoles, it's like the second child in the family, but there are no first one anymore. So okay, these are going to be the dominant force here, so to say, to create all kinds of effects. And this is exactly what is happening here. And this is why you should appreciate also the electric dipoles, because they give you insight on these magnetic dipoles. There is a question, are they the same thing? And I think you know the answer. Are they the same or not? And in what sense are they the same? They are the same. This is a surprising thing. The magnetic field created by a dipole and the electric field created by idealized dipole are the same. But let's see this. Let's see that this happens. It's not, for me at least, it's not obvious a priori. And I think this creates huge confusion at the beginning of the theory. Because you have two dipoles that give you effects like in magnetization and polarization, which are similar, but one of them has a charge and one of them doesn't have a charge. So if you are Maxwell, it's not trivial to understand such a thing. You see some symmetry in the dipoles, but not a symmetry in the monopoles. It's totally bizarre, in my opinion. So let us look at the n equal 1, which is called the dipole term. Dipole. And it's very simple. We have this infinite series and we abuse it and we take only n equal 1 and we throw to the trash all the rest. And this is called the A dipole. So A dipole, and again, when will it be good? Approximation, we hope, and it is true, when the distances are large. This is a good approximation. So this is given by this ugly, still ugly expression. u0 4 pi 1 over r to the power 2, because now n is equal 1, so 1 plus 1 is 2, so this is r to the power 2, and now we need to integrate. I'll write this as a crooked integration. It's not a choice. You have r prime cosine theta prime dl vector. So this is not something so simple. This is not you know, what is this? What is this? I mean, a priori, I don't know if you can see what it is, but I cannot, or at least not in 9 o'clock in the morning at least. So what is cosine theta prime? Let us massage this equation. So let us remind ourselves it was over there. This cosine theta, you see from here. So again, maybe you want to draw this again. So you add r, then you have r prime, and this is theta prime. So this is the origin. So this cosine theta, you see, I'm going to take not the vectors themselves, but their unit vector of these two guys. That's a definition of, this is hat. So this is a vector of 1 unit length minus r prime, like this. Yes?
I think that it's not supposed to be a vector. R prime is not supposed to be a vector because if it's a vector, we get
Yeah, sorry, this is wrong. Thank you very much. So this gives you the vectorization of this. So we have this product here, and then, okay, this doesn't really help. Let's write it still. Dipole, this is u0 I 4 pi 1 over r to the power 2. And I'm just rewriting. And okay, there's a small issue here. You see, this is not a vector as he just pointed out, and this is a vector, so I was correct, but not really, I was wrong. But r times r prime, vector is the vector. So now we have this strange loop to integrate over, and then we have r hat, this one, and now we have the vector. This is not a mistake, this is correct. This is giving you this cosine theta times r prime. I hope you can all see this. And then I need to integrate by dl. This is also an ugly equation, in my opinion. But then some small magic happens, or big magic, depends how you are used to it. This can be simplified. And I'll just give you the result, and later we will explain why this is the case. So I'm just announcing the result. This I dipole, dipole, which is eventually what we are going to use, is mu 0 4 pi 1 over r squared m cross r. Okay, this by itself is not good enough. So here is r is the distance, the vector, the distance, and here we have m. So the 1 over r squared is easy to understand, all these prefactors. What is m? M is the magnetic dipole that I'm going to define now. What is it? What is this m? This is the important issue, in fact. This m, yeah, I got... yeah, right. No, sorry, there's no I, this is part of the M, of course. So, yeah, sorry. So, this M, what is this M? And then we need to understand it a bit from physical point of view and then mathematical point of view. What is this M? M, by definition, is a vector. It's I integral over the surface. I'll soon, I think you know what I mean by this, or most of you, ds. And this is also written sometimes as is. So what is this integral? What does it mean? It means the following. I have this complicated wire in principle. I have the I. This I is the direction of I is important because it defines with the right hand side the direction of these ds's. So with the right arrow now it will go out of the board. You have here some delta S1, which is a vector orthogonal to the in plane, and you have to sum the delta S, delta S, delta S, delta S, delta S, And what does this give you? It gives you the area inside with the vector outside. There is a small issue, maybe or not, I don't know. What is the meaning of the surface here? Is it an obvious definition of a surface? If I have a loop in a plane, the surface that you most likely will choose is in the plane, right? But if this is a crooked object, you might not be well-defined surface. So we will soon show that it doesn't matter. You can choose it in principle how you want the surface. You can build it outside of in a complicated way. If you are not so smart, yes. And the result will be the same because of cancellation of the summation of the delta S. I'll soon give you an example. But so my point here is that the definition of the surface is not totally clear, but in most simple example, it's obviously clear. In general, not, but we'll soon show it doesn't matter with just some examples. So we have this S. Okay. So why does this happen? I mean, the way I remember this, what do you see here? You see that the S, I mean, the I is trivial. That's why I forgot it before. The I is trivial. The more current you have, the bigger are in Bio-Savart, the bigger are the magnetic fields. I think this is trivial. But why is this surface, this area, why is this important? One way to memorize this or to think about it in a simple example is the following. So I'm going to show you two examples. Let's take the simplest one, which is a loop, which is a square. And I'm going to write the I like that. And now I'm going to build another object whose circumstance is the same as this one, even though my plot will be most likely horrible, and the same I. It's a cross. In Bar Ilan, you're not allowed to do this. But, okay, so this goes down. This is the current. What is this area here? Something. A squared. What is the area here? If this goes to 0? What is the S here? 0. I mean, if it will be like this. So this guy has no S, this guy has a big S, this guy has a magnetic moment, this has no magnetic moment. Why does it make total sense? It's very simple. Let us now think about some point, let's say here, the same point here, the same distance from the center. What is happening here? This current here, which is close to this current, they will cancel each out when they create the magnetic field because of Bio-Savart. They are one on top of the other. If you have two currents going, one going there and the other one going there, what is the current?
0.
Effectively 0. So when you become smaller and smaller, this is 0. And that's why it's obvious that, not obvious, but it is reasonable that the bigger is the S for the same current, for the same circumstance, you expect that the effect on the magnetic field will be stronger. And this is my intuition for this, a simple intuition. That is going out. So here, currents cancel each other. No M means no S. This is S, this is equal to 0. And then no A, which means no B. Far away. Okay, so this is the common sense here. Let us just check for sanity, and also so that you start thinking about it, that the definition of the surface is not important. And let us do it with an example, a very simple example, but it's much more general. So there is a theorem in mathematics. So the problem is a current in a loop does not describe uniquely a surface of the loop, however, it's not a real problem. S is independent of the way we construct the surface. Okay, some mathematicians will struggle with this. I mean, I don't mean surfaces that cross each other or something crazy like that. Surfaces that start at one end of the loop, end at one end of the loop. Let's not be true mathematicians and not pretend we are. This is what I mean. There's no crossing. So, for example, if I have this object that I had before, and this is A, and this is A, this is A, this is coming out of the, so the Z is in your eyes, pointing outward. This dot means there's an arrow pointing in your direction, so that is the direction Z. So it's obvious that what is S is A squared times Z. I mean, this is the normal choice that we just choose the surface in the plane. Now, if we are a bit more ambitious, we might say, let us choose a different surface. Let's say this is the same object, but now I choose this object to be the surface. So here is A and here is A. Now I build this tent on top, and I say, okay, this is my surface. It's closed, it's going all along. There are two walls here and two walls here. And then we need to define this height. This is some definition of height. So this triangle, we have here a height. This is, I think I call it D. And what is important is this H. This H here. So this is D, this is A over 2. And then what is H? This is square root of D squared plus A over 2 squared. This is Pythagoras. I can calculate H. So if I know H, I know this area, right? So what is the surface here? The vector of the surface. So for that we need to understand the directions of that we are talking about. So you need to imagine also vectors that come out here perpendicular to these two surfaces. So we have this tent, the side of the tent, and it's going out. Now there's also in this direction, but you see this area and this area, the vector going outside, they will cancel it automatically. It's trivial that if I do delta S, delta S, delta S on this side, on the opposing side, it's exactly the same with the different directions. So I need to consider only the sides here of the tent. I think this is obvious, and this is not the same because this is 90 degrees and these are with some angle. And okay, what is S? S is, this is A times H, they are squares, times N1 plus A times H N2. So again, what is for example N1? This is a unit vector perpendicular to the surface on the right. This is 1 and the other side is 2. So I think it's obvious from symmetry that S is something, we know what it is. I mean, it should be this A squared times Z, right? Because these two vectors, they have components in the Z direction. This Z is now in this direction, and they have components in this direction, but those components are direct. So at least this Z and this Z is trivial. And if you define, it's very easy to prove that this coefficient is going to be, this is going to be A squared, of course. And to prove it, you just need to use simple geometry, really high school geometry, in the following way. So we have here theta, and we have this vector, which is this n1 here. And then I can have here, this is going to be theta, this is 90 minus theta, so this is theta. And this one is a over 2, and this is h. So I can easily find cosine theta. And cosine theta is a over 2 h. And the h is downstairs. And it's important that it's downstairs because eventually it will cancel this h, which is upstairs. So n1 plus n2 is 2 times cosine theta. Again, theta is this angle really. And this is equal to, you see this 2 is also cancelled by here. So there are two vectors, and this is because this is a over 2, so this comes here. Okay, good, it's cancelled. And this is given by times z, as I said before, a over h times z. And then, as expected, s is, you see this h is cancelled, a squared over z, independent of the choice that we did to define the surface. But there was a difficulty, the real difficulty in my proof. Up to now I just gave you the result. I just said, okay, this is m, but at the beginning we had this r dot multiplied by r prime. This is not too complicated, but this is more complicated than what was said here. By complication, I mean you need to use some algebra and some known results. Basically, this is based on the Stokes law. To prove this, I will give you some of the proof, or just so you get a feeling what type of tricks you need to prove the...
Sorry, Ellie?
Yes?
Just someone asked if you can write with another color so they can
Yeah,
see.
but my black one is dead. And the green one, I just took it randomly. I only have green.
I
I
have
have
two
red.
black ones if you want.
Yes?
Can you
Oh,
pass
thank
down?
you.
Sorry?
Yeah, I'm sorry about this, guys, at home. So, okay, so let us prove... Okay. Okay. No, I don't have any. So now we want to treat this R prime vector. It was defined here, this issue. And so we are going to add a new equation that I'm not going to prove at the beginning. If I have time and patience, I will prove it later. This is based on the Stokes law, and that is the following general equation. If I do an integral over some loop, t dl, then of course if t is independent of the coordinates, this will give you 0, but t is some scalar, whatever you want, but in principle depends on coordinates, so you can think about it going over this loop. This is this integral over some loop, and this is equal minus div t cross ds of the same loop over the surface. So I have a loop, I have a function t, and I integrate it over each point. The t is something else. I integrate over this loop, I close it, and instead of doing that, I can do this. I can take this div of t and cross L. Of course, both sides are vectors, in principle. Of course, if t is a constant, this is 0. And what is this one? Also 0 because of the derivative. And also you see the units point of view. Here I have an integral over length. Here is a surface. Here is the div. So these are like, in some sense, they are a generalization of integration by parts if you go backward, or one integration. What?
T is a scalar field, right?
Yeah, t is some scalar, there's no vector. Why is it a scalar? Because I'm looking at this object really, and this is a scalar.
Okay.
This is why I choose this formula, which again, it's easy, it's not so difficult to prove. So, okay, so we want to choose this, actually, I'm going to use this one. So you remember, what was our hat? This was this cosine theta that we had. And then I had the r, so now it's going to be the vector. But this is again, this is a scalar. The scalar has an r. This r is not part of the integral, right? Because r is just the position of the observer. This integral over dl is related to this r prime. Because, yeah, if you want to add a prime here, then it is fine. So I have here r, so the r is fixed. And this is this vector, r prime. So if this is correct, and I'm just using this, then I have r prime r dl. This is equal to, just copy this, over the surface. Here I have r prime, and this one is with respect to what? With respect to r prime, yeah? Because as I said, r itself is just the location of the observer. So this is the definition of this divergence cross ds. So now I need to look at this object. What is this thing? That's easy to do. R prime vector, and this is with respect to the prime. So this is div. What is this object? I can write it like the following. I'm going to write it as r vector over r. This is just the vector r prime in just in usual coordinates, I mean Cartesian coordinates. This is simply r minus r average, and here I have, of course, okay, let us write it, x prime plus y prime, y plus z prime, z. This is simply the r prime, and you understand, I hope you can see this more or less. When I act with the div, I act only on this. So what will happen? Let's look at what happens when I use the first term, and this guy will simply go away, and then I multiply it by x. So if I do this, I simply will get this is equal r hat. That's, I think, easy to solve. Yeah, because the derivative goes, and then you get this r hat. And then we are done more or less, because we had before this integral, which I called ugly, when we calculated a, and I replace it by this m. But this is more or less this. You see, what is this ds here? This ds here is what I'm going to what I'm eventually going to use for the magnetic moment m. And so you can more or less see this. So we have here r hat. The r dl is equal to, it's actually minus, you need to think about the signs, r cross ds, and this is equal, now I can do the integral, it's integral over a surface, and I can change sign, it's s cross r. And I guess S is the vector, is a vector which describes if this is the current, it's a vector pointing in this way, and it's the area of this thing going outside. This S was proportional, of course, to M, and everything follows from here. From these definitions, of course, you need to multiply by mu0 over 4 pi, etc., and you get what we got before. This is my point of view. Now, if you want to prove this one, do it as an exercise. Or if you are very interested, come to me in the break. No one will come, I'm pretty sure. But it's based on the Stokes law. It's like one simple page of algebra. So I'm not going to prove it. But yeah, it's very not difficult to prove. Okay, so now we have the basic theory, and now the question is, okay, so we have the leading term when we are far away, and then the basic question is, yeah, what is the magnetic field and how does it look like? And there is another surprise that maybe you're used to already. And what is the magnetic field? Again, neglecting all the correction terms and only the dipole. So, what is a dipole? And it's a dipole mu0 over 4 pi r squared m, and m has in it the I r. So we have some loop. Let's call this, let's look at the simple case. This is, okay, I want to idealize the dipole. What do I mean by idealize the dipole? Physicists say the following. We have some maybe complicated currents, but far away we have a dipole, so it's like looking at the Earth from far away. Instead of looking at the full structure of the mountains and valleys, etc., let us look at it as a sphere, and then we're going to take the sphere and make it a point. We do this all the time in physics. And this is more or less legitimate. When you are far away, if you want to be more mathematical, we are taking S to 0, right? And I to infinity in such a way that I times S, the size of the surface, is a constant. This is what we are doing. So this is what we call idealized dipole. And it's a very good idealization in practice, because usually we are not inside some matter. When we are not close to the source of the dipole, we are usually far away, because our machines cannot go into the material usually. So this is a fantastic thing to think about, this idealized object. And actually this is what we will do later all the time. So we can think about this idealized object as a starting point as a circle. That's even simpler, and then squeeze the circle, because this is just a loop, which is perfect. So we like this thing, and this angle phi, so think about this as the xy plane coming out, and this angle is the phi angle, and this is just the direction of the current. So, okay, so let us define, first of all, the m is going to be in this direction. We know the size of the loop is going up based on the right-hand rule. And we are looking at some point R. So it's most natural to define the reference frame in the middle of this object. And we have this angle theta. This is the usual spherical coordinates. I use this to define it. It's obvious. But this is not theta prime. This is theta. This is defining the position of the observer. Okay? So here is my guy who is looking and is interested in the vector potential at some point, and later the magnetic field, and then this is by our approximation. Okay, it's given by this equation, which is m is in the z direction, right? R, so you immediately see what is m cross r. It's related to this theta, because this is a vector potential, a vector multiplication. So the answer will depend on the sine theta. That's pretty obvious. So we have u0 m Don't confuse it, not with mass and not with the quantum number m. So this is the size of the magnetic moment in absolute value, where I define the direction. Well, you don't need the m, I mean, it's just m. M means the size 4 pi r squared. So again, usual potential decay is like 1 over r, the dipole decay is like 1 over r squared, the usual stuff. And here I have sine theta times phi. That's the point. Because of this cross here, it's in the phi direction. So, for example, if this is the plane, and here is it's in the plane, then if I look in the plane, how does this thing look like, this vector potential? It looks like something like, it depends on r, so maybe I'll bigger distances, but it's rotating in phi direction in the plane. I hope you see this. So this is in xy plane. So it circles, right? I think you can see this from this equation. Why does this make sense? What is the rotor of this?
Zero.
No, opposite. Well, first of all, this is only in this plane, right? So it's not a constant generally, but you immediately see that the rotor of this is not zero, and if I just use here, it's going to be in the up direction. That is the magnetic field that will be created from this A. But this is the shape, and there's symmetry with respect to phi from obvious reasons, because the source is in the xy plane, so the rotation around phi is meaningless. So yeah, from here, this is the A. It's very different. First of all, it's different from the electric field, that its rotor is zero from a charge, but we should not compare electric fields and vector potentials, maybe you say. But the point is that it's obvious that the KL is not zero in general, and soon you'll say, what is the thing? So, okay, so I take this A, again, this is A dipole, it's an approximation, and then yeah, you can easily calculate the B. So the B dipole is the rotor of A dipole, and this is given by U0 m 4 pi 2 cosine theta. So it's not so elegant maybe, but it is what it is, r to the power 3, because this is r to the power 2, r to the power 3 again. Like dipoles, plus sine theta r to the power 3 theta. So we have these directions, which I hope you know. You know, this is r theta, this is theta is like that, and phi is like that. So I hope you know what are the meaning of these r hat and theta phi. This is just the usual definitions of the of this thing. So just for sanity, let's say theta is equal 0. So what is going to happen? This term will go away, right? If this goes away, what is cosine theta? This is the z component of this thing. So going back to here, we had the vector potential was these circles in the plane, and at least along here, as was said before, this is the magnetic field along this line, right? Because, and it decays with r 1 over r squared, so this is theta equals 0. So these are the A's circling in the plane, and then the B goes, there's no component in the theta direction. On the other hand, let's say theta is equal to pi over 2. So we are here. So this guy is 0. And this sine theta is 1. So here we have sine theta is 1, so this goes downstairs. So how does it go here? This is so the point is that theta is what? What is, it's not here, I mean theta doesn't continue like that. Theta here and here is the same thing, because theta is between 0 and pi. And then it's obvious that the field here and here are the same. So when I go from this point to that point, I'm rotating in phi actually. I'm changing phi, but this expression is independent of phi. And then we eventually get that here it also has to go downstairs. And then if I'm down here, this is theta equal pi, then you have your cosine theta, which is minus, so you go up here. So, but what is really important is this expression is exactly the same like the dipole of an electric dipole. So, electric dipole, I mean, of course the prefactors are a bit different, but this is just a definition. Instead of M, we have something else. What I mean is that this is the same thing that we got for electric dipole. Again, idealized dipole, if you want, when you take the distance between the two charges, plus and minus, you squash them and take the two charges to infinity. This is exactly the same, and this is important, same as electric ideal dipole. Which, as I said, is not so trivial. And of course, it's also wrong when you go very close to the electric dipole. If you look at a real dipole, two charges, electric dipole, and you go close, and a magnetic dipole, they are not the same. I mean, not in the physical world, but this is obvious because there are many different types of dipoles, both with charges and with magnetic fields. So you can have anything in short distances. But again, at large scales, these are exactly the same objects. From point of view of the generation, of course, the effect of if you have a charge, the effect of B on a charge is very different than the effect of E on a charge. This is obvious from Lorentz equation. So eventually what we get as a magnetic field, so here is an idealized object. So here, as I said before, we have some lines that are going inside, and then this will be going out, and then this one will be closing here. This is this minus here. I hope you understand these lines. This is also going down like this one, and yeah, these are the magnetic fields. And the way to see this is a cut. So if you rotate it, you'll have the phi symmetry is independent of phi because of this thing. So this is a cut. So yeah, this is going down, and then here we have, it's symmetric. So you have something like this. It's a bit difficult. You need to think about this a little bit. Okay, so to summarize, we did this dipole approximation, and we got the same dipole as the electric field. And now we have dipoles. And what do we have in real material, macroscopical material? Maybe here we have many dipoles in principle. What are these dipoles? These are atoms. They have dipole moment because they have spins. Magnetic dipoles are everywhere. They have spins. You can think about, if you want to think about it more classically, let's say look at the hydrogen atom in a classical view. What is that? Neglect radiation. It's just Earth, Sun. So the electron is rotating. It's rotating. It's a dipole, a magnetic dipole. It's not By the way, it's not an electric dipole because of symmetry. If the charge is uniform, if there's no external field, it's not. But so the dipole, if you think about this in a very simplified way, because this is not exactly correct, you know, hydrogen atom, but any atom, you have a charge in the middle that is sitting, and you have a charge here, and it's moving. Even though that does not really define a current when relativistically, but let's say this is a current. That's a magnetic moment. It's not an electric moment in the sense that the electric moment is moving all the time and it's averaging to zero if the motion is fast. But there is a magnetic moment. So maybe that's the reason why magnetic moments and magnetic dipoles are in some sense even more important than electric dipoles. But I don't want to say they are more important because from conceptual point of view they are both important. But what I meant by this is that in nature, many times you see a lot of magnetic dipoles easily. Of course, you can see also electric dipoles. It's not that both of them exist. But in a natural way, every atom has its own dipole. That's why they are important. This is not related directly to electrostatics. It's just related to the way atoms are built. I mean, so we are going out for a break for 10 minutes, and then we will treat magnetic fields in matter. We will bear some similarity to polarization. There will be some similarities, so I'm not going to go in all the details. And that will be after the break. So now we want to discuss essentially magnetism in matter. It's slightly similar to what we had with polarization fields. When you have dipoles, electric dipoles, but there are some major differences. But the structure of the theory is the same in the following sense, that the same questions that we ask here are the same as we asked before. But there are some physical surprises that we will discuss briefly, but we will not really solve, because to solve these puzzles we need microscopical theory and actually quantum mechanics. So what is a magnetic matter? You have some material, think about it as a three-dimensional object, and inside we have atoms or molecules, whatever, but you can think about them as some dipoles that are rotating in some directions. And in usual materials, but not in all materials, you will have, you see what I plotted here, it's coming out of the board, so you know, with the right hand side it's coming out, the current is in this direction, but here it's in the opposite direction. So the atoms will be organized, let's say in a gas or even in a solid, in all kinds of different orientation. This is not a usual solid, this is a disordered solid. But even a lattice has different domains, and they will be all organized in all kinds of directions. And then what will happen, the total magnetization, what is the total magnetization? Magnetization, I'll just sum up all these magnetic moments together, it will just give you zero. So, and this is what usually happens, but not always, I'll soon discuss this. When B is equal to 0, there is no preferred direction for the magnetic moments, the microscopical magnetic moments, and they are all oriented. But now if you switch a magnetic field on, you might expect, or you may not, I don't know, that all the material is now looping in the same directions, because there is a kind of preferred direction, and here we'll have magnetization. What is magnetization? It is the macroscopical effect of many small magnets pointing all in the same direction. But this picture is very similar to what we had with the electric dipoles. What happens in reality? Now, of course, we need to ask the question, given this magnetization field, how do we define it? How do we define effective bulk currents, and we will have currents on the surface. We'll have a lot of mathematics that will come soon. But before doing that, what is the most basic phenomenon that you see in laboratory? Based on this picture, as I said before, this is similar to to electric polarization. So remember, this is the polarization field, electric, right? This is these small dipoles adding up, electric dipoles now. What do we know about them? They are proportional to something times E. And what is this something? Yeah, it has a name, but I'm even asking a simpler question. Is it positive or is it negative? It's usually positive. And now we ask ourselves the question, will the same phenomena happen for magnetic moments? And the answer is no. Sometimes this constant can be negative. Sometimes it's positive. And this is a surprise. I'll explain again why it is a surprise. But anyone wants to say why it is a surprise? What argument will say, oh, they all should point in the direction of the field? What simple argument? I'm not saying it's correct, because obviously it's not correct, because we find in laboratory something else.
I expect that they will align.
Yeah, but why? What is the basic rule? Very simple rule. Energetic rule, because the energy of the dipole is magnetic dipole and electric dipole is such that it prefers to align to get the minimum of energy in this direction. So something more is going on. We don't know what is going on, and I promise you by the end of this lesson you will not know exactly what is going on, but something interesting is going on, and you can think about it like this. And like when Maxwell and all these guys were thinking about it, there was no quantum mechanics, and they had to struggle with this. It wasn't obvious what is going on, and we have some hand-waving arguments for this, but it's a phenomenological theory. A phenomenological theory means we go to the laboratory, we observe things, and then we say something on this constant. Is it positive, big, small, depending on material, temperature, whatever. And sometimes, unlike electric fields, you will see here negative response. And so we have here all kinds of names that are always, at least for me, hard to memorize. So we have paramagnetism. This is a positive response. To what? To external, I'm not talking about electric field, external magnetic field. Which means everything aligns like here, positive. I'll soon define the math a bit more complicated, but then there is the exception. So the exception, let's write it in capital, magnetism, or not exception because this is found everywhere, magnetism, exception compared to most electric fields is negative response. And then there is a third class, which are called ferromagnets. And these are permanent magnetization. And these we'll have as children, because we can take these ferromagnetics and pick things up from far away. These are the magnets that people sell. These are very special in the sense that they depend on the history of the material. So you have some material in the long distant history of it. There was some magnetic field that caused all the dipoles to align. Then this magnetic field has changed maybe many times, but the system still remembers this initial history and it remembers it forever. It's not related to energetic considerations because I can change magnetic field, so it's kind of out of equilibrium phenomena, where you have some breaking of the symmetry due to the history of the material. So ferromagnets, I mean, these objects exist for electric dipoles, but they are rare. They're very rare. Ferromagnets exist for magnetic. So as a concept, they are not different from parallel electric fields. The diamagnetism, as far as I know, maybe there is some exception, but it's super rare. There's no analog to the electric field. So there are different types of materials that we have. So why is diamagnetism surprising? This is what was said here. I'm not proving this, but the proof is simple. Similar to an electric dipole, the energy, this is the potential energy of a magnetic field is, of some moment. This is not mass, this is the magnetic moment. This loop, it has a surface, this is the magnetic moment, dot B. And it's exactly like electric moments where we add, that's why I'm not proving this, maybe I didn't prove it also there, but there we add the electric dipole and electric field, right? It's the same, very similar. And this is why if we say, oh, energy is everything, we expect it to align, and we do not expect these negative response, but we do see them in the laboratory. So aligning with field of what? Of the magnetic moments is what to expect. Based on what? Minimization of energy. That is, what we expect is that you are sitting down, you're not rolling here in the room, and the reason is that you have some swing, eventually it dissipates, it goes to its minimum of the energy. I'm not talking about effect of temperatures and things like that. So this is the surprise. This explains why this is not a trivial statement. So how can we justify this? The answer, as I said, is you need a deep theory, a quantum mechanical theory to explain this diamagnetism, but people had to explain it somehow in a classical way. And this is given by Griffiths. I'm going to explain this hand-waving explanation, and you can decide if it's a good explanation or not explanation. It's not there is no global explanation, because it's not that all the materials are like this or all like this. It's a hand-waving argument, what is going on and where it comes from, this negative response. And it will also help us define this a little bit better, and let us see if I don't make a mistake. So I want to consider a kind of simplified model. This is a proton, this is an atom. So again, there are tables. Let's say hydrogen is diamagnetic, and other material, I'll soon give you some examples, are not. So let's look at this simplified version of the hydrogen atom. So what is it? You have an electron and you have a proton, and let's say the velocity is in this direction, so this is a plane and it's going like that. Of course, when you have matter, so I have many of these guys, of course. Some of them, let's say, will go in this direction, other one will go in this direction. So I'm choosing now one direction, and let us see what happens, and then we'll have to choose the other direction and see what happens, and calculate it. So again, it's not that, so the way I see this is you have these loops, some of them are like this, some of them are the opposite. This is when B is equal to 0, and they all cancel out somehow, and then, but now I'm looking at one of them, and we are adding a field. They are not interacting one with another. So let us think about still here, B equals 0. Where this is in the plane, which direction is the magnetic moment of this object? So we have the velocity is in this way. Right hand is up here, but where is the current? It's a negative charge. This is M0. It's going down. But this is just a definition. I could define it up if I would reverse the field. Now I want to add a magnetic field. So the magnetic field, I'm going to define it in this positive direction. This is why I choose this direction, and M0, the charge is negative. This is the plane, and it goes down. No, because this guy is going out of the board. Is this better? Sorry. Okay. It's the opposite of B, so this thing is out of the plane. Okay, so now what happens when B is not equal to 0? Let us imagine that what happens when something happens to what? We're going to assume the following. It's a very strong assumption. The radius here, some radius, it will not change. This is the size of the atom. The magnetic field is very small. There will be some increase or decrease of what? Of the velocity of the particle. Let's assume that it increases. So if, now it's an if, but soon we'll hand wave. If velocity increases, what happens? Magnetic moment in absolute value increases, right? Why? This is trivial, because simply if the velocity increases, then the current is increasing, and then the magnetic moment is increasing. So if we have a situation where the magnetic field increases the velocity, then you increase the magnetic moment. So if this is correct, then we have this thing, and now instead of this thing, what happens to M0? This is without the field. I'm exaggerating, of course. I increased the magnetic moment. So increase the magnetic moment. But what does this mean from the point of view of response? The magnetic field was up, and what am I looking? I'm not looking at, this is of course bullshit, yes? This was the M0. Actually, it is a very small addition, but the delta M, so this is MB, let's call it, M with magnetic field. The point is that MB, let's say absolute value, minus M0 without the field is bigger than 0. This is what I called response, negative response, right? Because the new addition comes negatively. This is how, I guess Maxwell and all these classical people looked at these things. But the question, another question is, does it always happen? Does it always increase or does it not? The answer is there is no, actually, it's not so. Okay, so I'll give you an argument why it does increase, always, but this argument is based on some assumptions that might be wrong or not. So you have to take it with a grain of salt. Now, so let us assume for a second, just to think about it, the velocity always increases in this picture. Then what is the problem? What is paramagnetism? So the answer is most of the paramagnetism comes from the spins. You have spins, and there's no current like I plot here, quantum spins. And then this equation is valid. And then if this is the dominating thing, then you'll get the usual paramagnetism as a spin. But if this is what happened, in some cases, if that effect of the diamagnetism is stronger than the effect of the spin of the electron, so in this picture I didn't have an electron, right? I mean, I didn't have a spin. So there are two different mechanisms. One is the increase of velocity that may happen due to the magnetic field of the orbital motion in the classical world, and the spin, which is totally quantum, which always prefers, you know, this is like Zeeman effect in quantum mechanics. This is correct. And what happens? It's a jungle out there. I mean, I know that you are in physics, people like to give you nice pictures, everything is the same, but it's simply not true. There is a phenomenologic And this is very important. For example, in phase transitions, the material can go from one phase to the other. So this richness is I hope you're not thinking about it as so complicated. It's very interesting. I mean, this is the way we think about it. It's interesting that it is a rich problem, which is going beyond electrostatics. So what is the motivation for this increase in hand-waving way is we can do a back of an envelope calculation.
Can I ask a question?
Yeah.
When you're saying small magnetic field, it's small compared to what?
I meant, first of all, the following. I meant that the delta M here is small. So when I say, for example, magnetization, what I'm thinking about is linear magnetization. So I apply a small field. Now, what is its small? I'll show you now. In a classical world, which is maybe not correct. So, okay. So let us do this calculation in a classical way. Classical thinking. So, for example, when I was a student a long time ago, I went to the first year experiment. I did the Zeeman experiment, and the instructor could explain me the Zeeman experiment based on classical ideas. And later, when I learned quantum, I thought it was crazy. But now I'm doing the same thing. I'm trying to explain you something without quantum, but some arguments, or which are most likely not correct. So, for the hydrogen atom, what do we have? We have a balance of forces. So what are the forces here? The forces are Coulomb force, and what else? Later we'll have magnetic force, and we have the famous MA, right? But this is radial motion. Let's assume it's radial. So what we have here is E squared R squared plus E V B, okay, I'll soon explain what is this, times B equal what? mvb squared over r. This is the usual radial acceleration that you have in high school, right? So this is what happened. And what is VB? VB, we have V0. This is no magnetic field. And VB is with a small magnetic field. And again, what am I looking for? I'm saying it will increase a little bit, V0. The difference between VB and V0 is going to be small, and it's going to be linear in B. Just some simple perturbation theory I'm going to do here. So first of all, if B is equal 0, then E squared over 4 pi epsilon 0 R squared is equal m V0 squared over R. I'll write this with capital R. R is the radius of the motion, right? This is just with B equals 0, and this is obvious, I think. Now, when you apply a field, okay. So first of all, what is really important here, and it is really important. This sign, I think, is obvious. I mean, this is just saying that the Coulomb field is attracting, right? It's a plus here because you have a plus charge and minus charge. But this thing, let us look at this. This is this. The velocity went in this direction, if I remember. So you have a magnetic field now in the z direction, right? So V times B is outwards, but Q is negative. So this is the Coulomb. This is Coulomb. The point here is the direction. This is what I care about, and this is Lorentz. It's also inwards for this choice of velocity. And that's why we have a plus. This plus is super important. Why? If I change the direction of the velocity, it will be minus. But what will change with it? The magnetization. The original magnetization will be up. So you need to do the calculation also with the opposite side. But that we will not do. So here I have a plus, and this plus is important. And then what do? I say the following. I will say that VB is V0 plus some delta V, and delta V is a small change in the velocity, and what we really care about is how much delta V changes. So what is delta V? It will be proportional, obviously, to B, to the magnetic field, because this is perturbation field in B, so this one will depend on B. And then let us see this. So this is 1 over 4 pi epsilon 0 E squared over R squared plus E V0 plus delta V B times B. And this is M over R, and then M is the mass. Maybe ME is better, not the magnetic moment. ME. Here I have V squared. I'm squaring this thing, plus 2 delta V squared, and there is a delta V squared, but I'm killing it because it's a small delta V. This is the perturbation. Now, I assume that R is not changing, which is a cheat. This guy and this guy go away. What about this guy and this guy? Perturbation theory. It's something small times something small still, and then I kill this. Then this V0 will cancel. And then what I get is delta V, the change in the velocity, is REB, which makes sense in the following sense. The stronger is B, the bigger is the change. Divided, if I didn't make a mistake here, this is divided by M, 2M, the mass. And the important point, and you can check this, delta V is positive. This is all what I want to say. You increase your velocity, and then you go back here, I increase the velocity. So, indeed, in this simplified model picture, velocity is increased when field is added. Now you need to repeat this again for the opposite side, and again you'll see that the M up will be diminished, the response will be negative. So this is a kind of classical hand-waving argument for diamagnetism, which is not satisfying, but it is what it is. So we can see that in principle, at least, we can get this hand-wavingly this magnetism, but we can do something maybe better, and that is just look at it phenomenologically. We have these phenomena, let's define things, and this is what we are going to do now. So let us hurry up a bit. Now we want to formulate this. So, first of all, the magnetization. What is that? So we have some material, and we had capital P and small p, and now we have capital M for macroscopical magnetization and small m for the microscopical M. So we have here some small box that we put inside. In this box we have sum over delta Mi divided by N. What is N? N is the number of microscopical dipoles inside the small box. You think about this small box as squeezing, but still N is very large. This is the magnetization, which is a function of R in principle. It can change in the material from different locations in a very complicated way in principle. So what is diamagnetism? We apply a magnetic field from the outside, diamagnetism, is that M is proportional to minus something which is positive B. And paramagnetism this magnetization field is proportional to plus something which is positive B. And what is ferromagnetism?
Even for B equal to 0, capital M is 0.
Yeah, but we formulate it like this: b to the power 0. B to the power 0 is a constant or 1 or whatever, and it doesn't care about the magnetic field. This coefficient here, what the heck? That is the idea of ferromagnetism. Now, what do we want to do? Let's say now we have this magnetic field, so the magnetization field. Someone put here some loops and banged them with a hammer, and he gives me this field M. How do we calculate the magnetic field? Not this one, not the external one, the one that is created by the magnetic field. So now I start with a system where I have my magnetization. This is my magnetization field, and I want to know what is B here in principle. So what did we know from what happened when we had the same problem but with polarization? We had these bulk charges, right? You remember this? What was it equal to? Minus div P. Now what will it be? Anyone wants to get? Rotor, yeah, it has to be a rotor of M. So, yeah, so for polarization, I'm not proving it right now. We add effective charges. Wait, but what did you say? Let us think a bit what did you say? But what does it give? This was equal capital P. This is the big P. Now magnetization, we feel it will give us, this is intuition, right? It will give, you need a curl because magnetic field has a curl. Okay, so let's write here a curl of M. But this is a vector. What does it give you? Not P. It will give you some current, some effective current. And this current is going to be called, this was B, this was going to be called GB. Now this current is important because next lesson we are going to study Maxwell equations. And you have currents. But what are the currents? This is part of the current. What are the charges? Rho B, there's rho B, rho free, there's JB, there's J free. You need to understand these different types of charges and different types of currents in order to understand Maxwell equation, because all of them enter into Maxwell equation, which will be next lesson. So for me, this is the most important equation in this lesson, which is going to be used later. So let us try and think what is going on. So what I'm saying here, I have this magnetization. I can find this GB. If the rotor is 0, then okay, there's no current, that's okay. We will have another effect, which is currents on the surface. So there are two effects. There are currents in the bulk due to this magnetization, which are given by this, and there are currents on the surface. This we also add for polarization. We add something in the bulk and something on the surface. So the analogy, I think, is pretty clear. So let us give the statement. This is it's a theorem of physicists, which means it's not rigorous, but it's really beautiful. Okay, so the vector potential A of a material with magnetization M, which which is the function of the coordinate, which someone gives you this, how it was created, it doesn't have to be a linear system or whatever, is equivalent to a source, something that is creating the magnetic field, which is called JB rotor M. This is the statement that we already gave. And this is, what is this JB? This is called, this is a current density. It's not I, it's like before, current density, but it's not coming from free charges that are moving. Nothing is moving in space. So the way you think about current in a loop is, I have some electrons, they go like that, right? Here it's not like that. Nothing is moving in space from one point to another. I'll soon explain exactly why this makes sense. Nothing is moving, but you have current, which is kind of cool. And you have also KB. So KB, you remember KB was a current on a surface. There was K, there was J, and there was I. And this is the K, because this is effectively on the surface only. So there's a current on the surface, which is given by M cross N. So M again is given. What is N? You have a surface of a three-dimensional body. It has some N going like that, perpendicular. Each point has a different surface current, and this is of course a vector. So effectively what you do, let's say you know M, and then you have in principle this K, these two types of currents, and then you go back and with them you calculate the vector potential A. I showed you already how to do that at the beginning of previous lesson. Give me J, I'll give you A, then we know this. So, but the most important thing is to understand what is the origin of this current. Now, I'm not proving this because the proof is similar to what we had with polarization, and also there we gave only half of the proof. But if you remember, we proved that this is equivalent to the usual electrostatics. So this is of course a blessing, because I don't need to sum up all the dipole moments and look what they do far away. We need to calculate these currents and then calculate the vector potential A. So what is the general idea? Let us look at this, especially let us focus now on the currents on the surface. So I have some bulk material and it has magnetization, which means the microscopical moments are all oriented in some direction. Let's plot it like this. This is my chunk, and let's say I have a magnetization which goes like that, and like that, and like that. All of them, I hope you understand. So the magnetization is in this direction, all of them, for simplicity. So now I want to look, but there are more, there are also some here. Hope you understand this is in the plane. So if I look at this N here, for example, and I do a cut, what do I see? What is the current that I see? So this is a sphere, let's say. So I'll have something like that. And then I'll have these kind of small magnetic moments going all around, right? They can be squares, it's just for convenience, and this goes like that, this one goes like that, this one goes like that, etc. So now you can say, what about the current here? But this one is cancelled from some guy inside. This is the claim, this is not rigorous. So the current here will be balanced by another loop here, but this will create a current like that. In this example, you see this more or less as this is not a proof of this thing, but you can see it or imagine this happening, and this is exactly this statement, because what is M? M in this example is up. What is N? Outside. M cross N gives you in the phi direction, which is this current that I plotted here. So you can see or have a feeling for this equation without proving it, but again, the proofs are similar to what we did already previously, so I'm not going to prove this. So we have here this definition of these two new currents, current on the surface and currents in the bulk. Okay, great. So now, okay, for completeness, let us write down what is A in a formal way. This is simply equal to mu 0 over 4 pi. Curl, this is this one, of M over the volume. What is downstairs here? Like Coulomb, it's with power 1. This is integral over the volume d tau. This depends on the coordinate that I'm integrating on. Again, this was many times. So I used here the j as before. So if it's the same as before, why do I write it? Because before I wrote it for j, and now I need to also write it for k. And these are not exactly the same because one of them is a surface and one of them is a bulk, so I bother and write it down. And this one will be an integral over the surface only. So this is over the volume, the whole volume of this thing, and now I'm integrating over only the surface. With this one, m that depends on the integration variable and on where I am in the integration variable. Again, the usual Coulomb's law. This is multiplied by ds, so it's on the surface. So again, on the exterior of this horrible object. This is the answer. This is this k. Okay, so we have this. And now, what are we going to do? We're going to discuss in the time remaining displacement vectors. So you remember there was an E and there was a polarization. And now what we will have something which replaces the D, the displacement vector, it's called H, capital H. It's not Hamiltonian, it's H. It's a magnetic displacement field. And then we can discuss a little bit linear material, and then we are done. So I hope to make it very quickly, because this part is similar but different because of the currents in this system. But again, I am assuming that you know the polarization problem, so the magnetic problem is a little bit similar, but we need all these definitions to define currents, for example. So we define the displacement H. So what is the idea? We know that curl of B is what? Is U0, J free in general, plus what? J bulk. What is J bulk? Again, this is the rotor of M. You have some material and then you have these two types of charges. One of them are just free to flow, real currents. I mean, things that are moving from one point to another. And then you have this magnetization current. Of course, all this together is J. This is just J. So in some cases, at least, like before, we know what is GF. We control it, but we don't know GB because we don't know the magnetization. And then people have defined this magnetic field, displacement field, which is called H. So the idea is the following. What is this thing? This is U0, JF. But what is this JB? We just said what it is, rotor M. Rotor and curl are the same thing, of course. So I see here curl and I see here curl. So for free at least, we're going to put it together and then we'll get a simple equation, which is slightly useful, but it's kind of very popular. So the curl of what? Of B minus, yeah, I'll divide it by mu 0. This was also done with polarization when we got rid of epsilon 0. Maybe you remember, maybe you don't. So I'm going to define it in this way to get rid of this mu 0, which is just annoying. Over m is equal J free. The free currents that I control by voltage growth, something like that. So I'm going to define H, displacement field, as B, which is the real magnetic field, minus the magnetization field that is due to all the dipoles in the system. And then our equation is rotor H is equal J free. We are going back again to the usual Ampere law, but now with J free only, but instead of B, we have H. Okay. This by itself doesn't close things because we need a relation between B and M, which we can find for linear fields, but in general it's very complicated. So we have some remarks on this. So is H like a magnetic field? The answer is sometimes. It looks like a magnetic field because this is the same equation like Ampere's law, but it's not. Why and when? When is it different and when is it similar? I think you know this. When is it? Why is it not like a magnetic field?
Because the divergence.
Yeah, so it's related to the divergence, and this divergence of H is not necessarily 0, but under certain conditions on M, it is. And in those problems where the divergence, this divergence here will not be important, then you can say H and B are the same thing. But if it's not the same, if this doesn't happen, then they are really different objects. So I'm now classifying when this A apparently looking similar to B is really the same as B, up to constants, I mean. So div H, what is this one? Is like, this is the definition of H. It's div B by definition over U0 minus M. This guy gives you 0 because there are no monopoles. So what we see here is div H is equal div M. So if this thing is 0, so again, the way we think about it, someone comes and stucks all the dipoles with a nail on the board, and you can have different fields M, that depends on the microscopics. If this is equal, then you can say that H and B are very similar. By the way, they don't have the same units, but I think you understand what I mean. H and M have the same units, but B has because of this mu 0. But if not, then not. Then, however, if delta M is not equal 0, then be careful. Now, where is this important? Usually, I mean, okay, I can define a nasty question where the magnetization is very complicated, but in questions that come in exams, let's put it this way, where is this important? It's important on the surfaces. Because so this is the usual boundary condition. So you need to think about the boundary condition of H and be careful with it because there you can have jumps and things like that. But again, I discussed similar things in previous class, so I'm not going to discuss it later. So I'm just warning you, be careful about this thing. And of course, from here I can get this Ampere's law, HDL equal JF, and I can use the usual tools. So we can do that. So now, to close the loop, because just up to now it was actually more definitions than anything else, now we can say something on linear materials. Unfortunately, we cannot say much on nonlinear materials. So if the system is linear, which means that the magnetization, this is a linear system. It's proportional to B, it's proportional to H. but I'm not saying anything about the sign. So we define usually mu 0 m, which is a little bit interesting definition, because what we think about is the opposite, that m is created by b. But here the definition is we have m and I give you b. If you think this side is the function, of course I can invert it, it's not a problem, but it's the psychology of the people who started this field. So they knew something on the magnetization and wanted to calculate b, while you think I know that b and it's not clear, it's like the head of the mouse and its tail, then they are running after one another. But okay, but this is just a matter of definition. This is called the permittivity of the magnetic material. It depends on the material. This object is called 1 plus chi m. So in a vacuum, this is just this u0, this is the same as this u0 here. It's nothing, so this mu is some number that in the vacuum will go to 1, and chi m will describe the deviation. The bigger the deviation, the more you have an effect. So this means that m, it's easy to show, I'm not showing this, but it's trivial by taking the definition, is chi m h actually. Now I'm defining more precisely what is the meaning of this diamagnetism. Only now, I mean before these were words, and now we are going to define it. Now you can measure these things. You can measure this mu0 by different ways. I'm not going into the details, and then you can find this chi m. It's a very small deviation from 1 in most material, let's say at room temperature, in a gas phase. What I want to point out is that it is complicated, and this is diamagnetism. And it's only this deviation from the vacuum. It's not more than that. So, for example, bismuth, '79. This is the atomic number, and the odd number is some clue that something interesting is going on here. Gold, H, which is 1, 29, which is copper. I'm not going to write all of them, but all these guys that are diamagnetic are with odd for some reason. This is the number. It's a this is not equal. This is the minus sign. 1.6, 10 to the minus 9. So, oh no, sorry, this is for the hydrogen. But my point is, and the numbers are of the same magnitude, and this is for paramagnetism. So here we have, let's say, oxygen. Oxygen is 8, so the number of electrons is even. This is with positive. It's simply positive. I'm not going to write the number. The number is more or less the same like this one, but with a plus. And then you have sodium. Okay, you have all kinds of things, but here you also have odd ones, like sodium. Well, there's no rules. It's a jungle. It's not related simply to the number of electrons, and you're welcome to find a theory for this. People have looked into this deeply, but as a phenomenological point of view, we don't understand this so well. The only statement we can see from the experiment is that if you have odd number, then you are a diamagnetism. And the reason maybe is that the last one, you have a kind of free electron, and this is more or less the picture I gave you before. But this is all totally hand-waving. I mean, this is more, there are interesting things going on in nature that are way beyond this course, as it should be. I want to just stress the difficulty of the people who saw this for the first time, and later on there are solutions, but these are total different courses if you want to go into this direction. So now we are finished with this, and the most important thing for you to think about is about this JB, this KB, rho b for polarization fields and sigma b, because these are going to be used next lesson in the Maxwell equations. So what I'm trying to say here is that you know Maxwell equations, but introducing these materials introduce different definitions of what are the currents that go into the Maxwell equation. And I discussed some of them this lesson and some of them the previous lesson, and then we are going to use them the next lesson when we define the Maxwell equations in matter. So there are actually 3 currents, not 2. Up to now there were 2 only, but there are 3. One more will appear. And there are 2 effective charges, rho b and rho free. So read that so you will be ready for the next lesson. Thank you for your attention and see you next week. This is someone's בוודאי, כי מגנט אחד קטן של אטום הוא חלש ביותר, אז מבחינה פיזיקלית אתה תסכם על הרבה.
אין קטן למה, איפה המפרציה שלי? מה ההבדל בין פול חשמלי לפרופ?
זה גם שקול, כן. אז אתה בונה קופסה, מה שאני עושה פה בעצם, אני עובר לרצף. דיקול, אתה יכול לחשוב עליו בתור לולת זרם, כמו